This is a production of Cornell University.
All right. Let's go to the sulfur cycle. Sulfur cycle is a lot easier. It's actually a lot simpler in many senses. Okay, when we talk about the sulfur cycle, it doesn't look that much different than the nitrogen cycle. And this is the whole cycle, and I'm going to give you a simpler slide to look at. Okay, but basically what you're doing is you're looking at a cycle. Okay, we'll start with a plant here. Okay, let's start with the plant here. Okay, the plant is taking up sulfur, okay, as a nutrient. It gets harvested in whatever form, and this example that we're looking at here is we're looking at a cow eating it. Okay, that cow and the residual material from this organic material basically gets back into the soil. Okay, now we can be adding this material as fertilizer, or we could be adding it as an indirect stuff coming from basically acid rain, or we could be putting it directly as fertilizer, in this case as an inorganic fertilizer versus an organic fertilizer. Okay, it gets into here. What happens to it? Well, it gets decomposed, and as it gets decomposed, it can potentially be converted, actually sort of oxidizes. It doesn't actually be decomposed. It can be decomposed into sulfates, or it can be broke down into sulfides. Okay, now the sulfates are the only form that the plants can take up. So this is how it comes back to the plant. But this sulfate, depending upon what's going on in the environment, a lot of different things can happen to it. The sulfates themselves can be absorbed onto the cation exchange sites. Okay? It also can be leached. Okay? It also can oxidize in simple chemical reactions that have nothing to do with organisms and basically turned into sulfur. Okay? It also can be used as an electron acceptor for respiration when systems go anaerobic. That conversion turns it into a sulfide. Okay? This sulfide, when it is exposed to oxygen, no biological mediation whatsoever, will oxidize back into a sulfate. Okay? Feel comfortable with this? This sulfide also can be reduced or oxidized into a sulfur. The sulfur can in turn be reduced into a sulfide. Now we can get sulfides as well as sulfates from soil minerals, large pools, and I'll show you a slide in a moment that talks about that. Okay? The sulfate can be leached. The sulfide can be volatilized. The sulfide can be volatilized and then potentially taken back and brought in as acid rain, depending on how it's processed. Okay? We feel comfortable with that? Let's actually take a look at the pools. Atmospheric pool is actually rather small compared to all the other pools. Okay? The lithosphere tends to be the largest. Most of the sulfur that's in our planet is in the rocks. Okay? The hydrosphere has some stuff that's basically run off the land. Okay? The pedosphere and the soil organisms, stuff like that, they also have a fairly large pool as well. Okay? In the soil organic matter, and in the land plants. The sources of sulfur tend to be fivefold for the pedosphere. Primarily, it's coming from soil organic matter, the decomposition of that material releasing the sulfur. Okay? We're also going to see sulfur coming from weathering of that rock material. Remember, that pool is rather large. We also have atmospheric deposition coming through acid rain. This is coming out of coal-fired plants. We also have sulfur coming in in pesticides and in fertilizers. Okay, this is an anthropogenic source. Okay, some pesticides contain sulfur and it contributes to the soil, but its contribution to the soil is quite low. Fertilizers, once supplied, at one time supplied a lot of sulfur as an impurity, but today, because of the processing, sulfur, if they were giving you sulfur, they're going to make you pay for it. So they don't want to give it to you. Okay, so the purification processes are much better, and so sulfur is no longer really fertilizers are no longer really a source for sulfur unless you're intentionally buying the sulfur. Okay, and the last one is the irrigation water, and this depends upon where that water is or where you are. If the water is moving through the lithosphere, moving through rocks that have high sulfur content, and the rocks are weathering, that water is going to contain some of that sulfur. Okay, so it's really this groundwater, if you're getting it in your groundwater, that means the water is moving through rocks that have sulfur in it. Does that make sense? Okay, questions? Okay, 5 primary sources. Some examples, you've seen this slide before, in essence. I showed it with nitrate and I showed it with acid. Okay, basically we're looking at those coal fire plants and we're looking at downwind. Okay, the larger, the brighter the color, the orange the color, the higher the concentration. The darker the green, the less the concentration. All right, so those are the sources. What are the losses? Sulfur losses, obvious one is crop removal and uptake by the plants. So the plants take it up and then we remove the plant. Okay, when we harvest it, we're going to be taking the sulfur with us, or sulfur with the plant. Okay, we're also going to be losing sulfur through leaching. Sulfur is leachable just like nitrate. It just happens not to be as leachable. Okay, it will be moved out of that root zone by leaching. Okay, now just because it does not leach as rapidly as NO3 doesn't mean that it's not going to be lost from the system. So excessive rainfall or irrigation can remove that sulfate from the rooting zone down lower where the plants can't get it anymore. Okay, where are those pools when we start talking about the pedosphere? Okay, soil organic matter, and land plants. I have 3 different soils here. What you're looking at is the soil depth and then concentrations within each one and the profile. Okay, so you're looking at the larger the bar, the more the bar is over here, the higher the concentration. With mollisoils, high organic matter at the surfaces. Okay, high levels of organic sulfur at the surfaces. As you get into depth, you start seeing an increase in organic S in inorganic sulfur. Okay, the predominant form of the sulfur in these mollisoils are in organic matter, and the predominant area that it's in are at the surfaces because that's where the organic matter is. Okay, another really good example here is this oxysoil. Okay, you guys remember the oxysoils? Okay, very small amount of organic matter dropping off, not anywhere near as much organic S as we see in these, but you see a dramatic increase in inorganic sulfur with depth. Okay, the other thing to look at here is sort of where these numbers are. Okay, then we also have the spotosols. You guys remember? Question. Does the inorganic S increase because it's anaerobic? No, I think it has more to do with it's moving into the mineralogy, and well, actually with oxysols it's probably not mineralogy. It has more to do with just the movement of that material down. It's in the sulfate form. It's not in organic matter. Okay, there isn't a lot of organic matter down there. Okay, go.
Is sulfate organic or inorganic?
Sulfate and sulfides, they're not inorganic or organic. It depends on where they are. If they're in an organism, we would consider it organic. Okay, and the organic source, then we'd bring the organic matter and watch it decompose, and then it would provide the fertilizer in that sense. It's not, I mean, the biomass component of it, we consider it organic. And so this pool right here, the sulfur is associated with organic matter. This pool right here, the sulfur is not associated with organic matter. Does that make sense? So if you look at this scenario right here, because of the amount of biomass that's in this system versus this system that's actually in the soil, the sulfur in this case is not associated with, I mean, the vast pool of this is not associated with that organic matter, just because there isn't any organic matter. Does that make sense? Kind of-ish. Well, actually, let's take a look at this one then. Okay, this is the spotosols. Do you guys remember the spotosols? So those cool boreal forests, very bright E horizon, dark surfaces with BHs and BHSs down below. Okay, those are those reds and browns underneath a really bright albic horizon. Okay, well, if you think about how those soils are formed, they're formed through organic acids moving through the system, right? Well, those organic acids are stripping materials from above, the sulfur coming with it, and basically being captured in that organic acids basically sitting here. Okay? So what you're looking at here is the organic acids and the sulfur that's associated with those organic acids. Does that make sense? This is that BHS zone right in here. This is the E zone. This is the A zone, or an O potentially. So where is the sulfur associated with in these different soils? Mostly organic matter, mostly mineral material. Questions? Go, Lily.
Well, because like nitrogen, it can only be taken up by plants in the inorganic form, correct?
Nitrogen can only be taken up by plants with N fixation in the N2 form, but that's not the plants that are doing it, it's the rhizobia, or the ammonium form, NH4 plus, or the nitrate form, NO3 minus. Right? Those are, and in essence, those are all inorganic forms. The plants cannot take them up as in an organic form. The microbial population has to break down that organic form so that the plants can take it up. Okay, so the plants in this case, the plants in this scenario, they can't take this sulfur up. But when this organic matter gets decomposed, they can take it up. The plants can only take it up in the sulfate form, SO4. That's their only option, the plants. Does that make sense?
Yeah, but is SO4, I guess that was my question, is SO4 inorganic or is it?
SO4 is inorganic. They have to take it up as an inorganic form. Yes. Now I understand your question. Cool. The fluxes themselves, we've already talked about most of these fluxes, but the flux that's really mediated by organisms is actually right in here. The rest of this, except for decomposition, the rest of the changes in the form have nothing to do with microbial populations. The microbial population is basically taking it from the sulfate form and turning it into the sulfide form. And they're doing it for a very specific reason. They're doing it because there's no oxygen present, and they're basically using the sulfate as an electron acceptor for respiration. Bang. Now, there are a couple of very interesting sort of environmental systems that this process is very important to. The first one is coal mining. Coal mining, basically, they're digging out coal. Well, where does coal come from? It comes from the ground. It does come from the ground. But where was the coal originally formed? And don't say the ground. It was plant materials, and plant materials built up, okay, during the Carboniferous era, okay? They built up, and they were basically in anaerobic swamp systems, okay? A lot higher oxygen content of the atmosphere, lots of greenhouse, basically a greenhouse operation, the planet, okay? Lots and lots of plants dying in an anaerobic system. They go into wet systems, okay? I've got lots of organic material in a wet system. Well, what are the microbial population going to do? They're going to want to respire, and I've got all this food. So what they're going to do is they're going to use alternate electron acceptors, iron being one, sulfate being another. So as a result, all of this organic matter is enriched with sulfides. Does that make sense? A couple million years later, we come along and we decide to start mining it. Well, we start mining it, we bring it up, and we put it into the presence of oxygen. Now, that's okay as long as there isn't any water around. Because for biological activity to happen, it needs to have a certain temperature and a certain moisture. Okay, if I keep the coal and I keep it dry, nothing's going to happen biologically. So I burn it, okay? And we get these sulfides up into the atmosphere. Sulfides get up into the atmosphere, what's going to happen? Well, it's got oxygen and it has moisture. Forget about the microbial population. I'm going to have a simple chemical reaction that converts it this way. And if I convert it this way through oxidation, I'm going to basically make sulfuric acid. Make sense? Now, how about this scenario though? What happens to all the waste product from coal mining? Not all of it gets burned. In fact, mountaintop removal in Virginia and Maryland and West Virginia, a lot of that stuff basically gets dumped. Okay, and if it gets dumped in the presence of oxygen and it starts to rain, what's going to happen to that acid, that mine spoil? This is what's going to happen. And I'm going to make sulfuric acid, and I'm basically going to acidify all my streams. And I'm basically going to kill everything in my streams. Have you guys seen pictures of some streams and coming out of some of these mountaintop mining removals, and they're like bright orange. And the pHs are really, really low. And in fact, remember me saying that there are some scenarios where we can actually make the pH lower than 1, 0? This is one of those scenarios with acid mine waste spoil. Okay, another scenario. Do you guys remember this? The hydrosphere? There's a good amount of sulfur in seawater. Okay? If you go into tidal wetlands and things like that, yes, you have the tide coming up, the tide coming down, coming up and down, lots of organic matter. But the systems go anaerobic at least once every 6 hours, right? If the system goes anaerobic, what's going to happen to that sulfur? What's going to happen to this? System goes anaerobic. The microorganisms that are doing the decomposition are going to find altered electron acceptors. They're going to drive it straight to sulfides. The reduced sulfur. Okay? What happens when we start dredging up the bottom of our canals to make sure that we have enough distance between the surface and the bottom so our boats can come through? We're going to dig this stuff up. And what do we do with it? Generally, we can't put it back out in the ocean. We have to bring it up onto the surface. We bring it up to the surface. It's in the presence of oxygen and water. Now, when it comes up, these soils have a pH in the 8s and 9s. Within a couple months, we're looking at pHs that are in the 3s and 4s. Okay? It's an interesting scenario if you think about it. And it's a very simple reaction. Let's skip this one. All right. So what controls these fluxes? Temperature, moisture, oxygen, and sulfur. In fact, I don't have to do a lot to talk about this. It's the same things that we saw before. Okay? I have an optimum amount, a deficient, and a toxic amount for plant response. Okay? We have all different sources of sulfur into the system. Okay? And if I start throwing sulfur up through stack emissions or through volcanic eruptions, that stuff is going to get into the air, at which point I'm going to get acid rain. Okay? Another toxic effect. Finally, if we think about how sulfur is available in the system, and we think about that sulfur cycle, the available soil sulfur that can be taken up by plants is this pool right here. Well, what affects that pool? Certainly things that are taking it up, actually right here, going up to plants. Those plants then die and come back, or go into organic residual material, or that sulfur can bind with the organic material and become more available soil material. Okay? We also can have leaching, and certainly we can have erosion losses. We also can harvest. If we take that plant material, we harvest it, whatever we bring back will go into the system, but whatever we don't is lost. We can bring it in as fertilizer to make up for this loss. Some of it comes in with irrigation water, depending upon what the rock material the water's moving through is. We also have the rocks themselves that the soil is in. This stuff is weathering, bringing more sulfur into that soil pool. We have a number of losses here and gains through wet and dry deposition. This would be acid rain, for example. But we also could have volatilization of the H2S. That could be lost to the atmosphere. So in essence, if we think about that cycle and the available soil sulfur that can go into plants, we have to think about how we're controlling those fluxes from those various pools. And that brings us right back to that cycle. Okay. Interestingly enough, microbial mediation of this cycle is only here. Okay? Cool beans? All right, guys, be free. Have a great weekend.
This has been a production of Cornell University, on the web at cornell.edu.